So, let's start with a map of this presentation. We'll go a very quick tour around category theory and why it's important for functional programming. Can I ask you how many of you are kind of using functional programming right now? Okay, so it's kind of a beginner. And how many of you have heard about the word monad? And how many of you are kind of confident to explain what a monad is? Okay, nobody. I hope that it's really not that difficult. I hope that at least if it's not this talk, after this talk you can study yourself and understand better. So the goal of this presentation is basically not to let you fall asleep. And yeah. As a secondary goal, I would like also to have people start looking at functional programming and then studying category theory. And it's okay if you don't understand everything, and it's more like a quick tour than to raise your curiosity. But of course, I mean, yeah, I hope that you can understand at least the main point. Oh, let's go very quickly. This is historical. So what is a category theory? Very quickly is something about, it's called general abstract nonsense, which is not a bad thing. That means that is something that is general, is it abstract, and it doesn't have a specific meaning because it can apply to all the stuff. And the category theory is actually using physics, quantum dynamics, it's using mathematics, and also in functional programming. So category theory in Forza is very, very high level. And I don't know if you know this comic. It's called Kevin and Hobbes, one my favorite one. And there is this stuffed toy with a tiger that when some adult is present, it's always a stuffed toy. But when the kid is alone, then became alive. And so this is a kind of transformation. And at the end of the day, category theory is all about transformations. But transformation that keep some properties. So it's not just any possible transformation. And let's start with the definition. So to have what is a category, since it's category theory? So we have a collection of something called object, which has absolutely nothing to do with programming object. Something called arrows that kind of link objects between them. And arrows collect one object to another. And the arrows must also have a property that you must be able to compose them. Otherwise, I mean, if each arrow is absolutely not composable, it's not a category. But if all arrows are composable, then that means that they have also to be composable and also to have a associative property. And also there must be an identity arrows that basically applying the arrows to any object, it will keep the object that it is. I mean, it's very basic requirement, it's not much. So we can do a kind of, I live in London. So in London we have the underground, the tube. And we can imagine that objects are the station of the tube and arrows are the travel routes. And each arrow is connecting to station. And you can compose the arrows because you can go in the, so for example, if you go from Bond Street to Oxford Circus and then from Oxford Circus to Tottenham Court Road, you can compose those two arrows to have a high level arrows. And you can keep composing them. And this is already make a category. So it's nothing really difficult. And at the same time, also a functional programming language is also a category. But there is one thing that is you have to keep in mind is that types are objects, so not a specific instance, but types like integer or string or user or whatever. And function are morphisms. So morphisms is exactly the same as arrows. So this talk is always about arrows and morphisms. So you have string length, for example, is an arrow that take a string and return an integer, which is incidentally the length of the string. But on category theory, that is not really important. What is important is that you can compose with other arrows that take the integer and transform in something else. Well, one small caveat for functional programming is that differently from mathematical, we have these things called partial functions. So there are some functions that are undefined for some value. For example, if you take a function with the 2 value and divide the first by the second must be different from 0. Otherwise, you have an error. And the possible errors are what we call exception in our in Java, for example, or it could also be an infinite loop. This is also a kind of error. So this kind of means that there is, for when we talk about the category in programming language, there always this bottom type, which is a kind of a T reversed. That is, I mean, all function can also potentially return this bottom types, but for the sake of composability, we kind of put this apart, and we really don't want to think about. So this is very, very, I mean, if you are kind of used to object orientation, you know, there is this nice metaphor where an object-oriented, wrote language, I mean, application is a bit like of a living, like a garden or an aquarium, a fish tank or something like that, where you have an object that communicate each other, they live their whole lives, and they can transform. Okay, in functional programming, this is very different. You have also to change completely the method because it's something more like pipes and gears, cogwheels, stuff that really have to fit together, and it's completely, either it's work or it's completely unworkable. And in object-oriented, you really wanted to keep the state, the inner state of the stuff completely hidden, and use a communication. So when you communicate with, I don't know, connection DB, you say, you really don't want to know what is the internal state of the connection. You just want to say, okay, give me this, the user with this ID, and it will return the user. And you really don't want to know about what is run inside. But in functional programming, it's the opposite. Everything is completely transparent. You absolutely see anything that is running, and everything must work with the transformation. So in object orientation, we have inheritance as one of the most important, and polymorphism. In functional programming, we have composition. So we can compose things using other things, but we never hide what is inside. Finally, in object orientation, we have interface. In functional programming, we have type classes, and we'll go back on this. Now, the example of this talk will be in Kotlin, which is not very important. I mean, I could probably write the same talk with example in JavaScript, or Scala will be much easier, probably. But I try first to have the example in Java, but it's really hard to read. And the Kotlin is very nice. It's quite similar to Java, so usually people don't have a big shock. And differently, for example, from Clojure or Scala. And these are some the advantages on Kotlin over Scala for functional programming. So my suggestion is, if you really want to try a bit, maybe using Kotlin is a better idea than using Java. We don't go, I mean, through all of them, but if you know more. Some examples. So if you are not completely familiar, just a question, how many of you are more or less familiar with the Kotlin syntax? Okay, less than probably 1/3. So there is it's very similar to Java, but there is some caveats. There is no semicolon. The type with the question mark is a different type than the type without question mark. With the one with the question mark is nullable. The other one is not nullable, but you cannot assign one to the other. If you wanted to pass a lambda, you have a kind of easier syntax than Java, basically using brackets instead of the arrow notation. Instead of in Java 10 they are adding the var, but in Kotlin there is this two-way to declare a variable if it's mutable or immutable, which is quite convenient for functional programming. And you don't need the new keyword. If you just have to create an object, you just use the type and pass the parameter. Yeah, yes. Okay, but why bother? I mean, why we want to to use an object-oriented language for doing functional programming? And well, I don't have an answer for that, but you have to keep trying. It's a good question, and but I hope that at the end of the presentation you have some ideas. If you are using Kotlin, there is, of course, you can implement everything yourself, but there is already a library which is already ready to do all this example of this book. And finally, there is a proposal to add type classes and kindred types to Kotlin, which is two things that we'll see later that were quite convenient. And at the moment, they are using a kind of a hack to make it work. Will be much better to having implemented in the language, and there is this proposal which also I'm collaborating to. So if you have some specific question, we can discuss later. Okay, so purity and immutability. You know how many of you know what a pure function is? Okay. For pure function, we intend a function which has no side effect. That means that whatever are the input, they determine the output. There must be no access into internal singleton, internal state, external, even print line is technically a pure function. And of course, when we talk about this kind of composition and mathematics, all the functions must be pure, because otherwise we cannot be sure that the same input give the same result. And so all the laws that we'll show are not working. And for the same reason, we have to use all immutable data. So everything that must be, we cannot use map that we can change. So each map must be a specific immutable object. And then if we wanted to change something, how we do? We just create a new map with just one value different. And then there are some tricks, so it's not so inefficient as it sounds. But anyway, just keep in mind that this is very nice and everything, but at the low level, everything is still completely mutable and impure. So all this stuff that we wanted to do, be mutable and purity, is only because we wanted to compose them. It's not a value for say. But we'll go back on this one. So the first thing the first beast that we'll talk about is a monoid. So basically, we saw this this example of a category. So, but what if we do a category of all the arrows, all the morphism of a category? And basically, it looks more or less like this. This is just to think about. So you have a types, and you kind of collapse all the types in a single object. and then everything that works on the types basically stick working on the same object. So you have a category with just one object and a lot of arrows that works on that object. And so when we have these arrows must all be arrows of the same kind of type, like for example the incremental. So we have something that take the object and return. And this kind of a composition, so if we compose the one incremental with the second incremental, we have like a +2, or we compose again, we have a +3 and everything. And this is also quite interesting because theoretically this is how they define the set of natural numbers from logic to category theory to mathematics. But this is quite theoretical. But we have this idea of monoid. So monoid is something that allows to compose arrows. And if you want to really squint enough, we can also say that the tube map is a kind of monoid because it allows us to quickly compose arrows between places. It's not that difficult. And when we have in the code, let's see how we have something that if it's a monoid, it must be something that allows to combine and have an empty value. So the empty value is the beginning, so we can start. And we have something that allows us to combine two arrows together. And we see some code example. But first, let's go back a second about this discussion about the type class and interfaces. Interfaces, when we have an interface, is something that we have two types, cat and dogs, and we say they are both animals. And what can you do with the two animals? Probably they can mate each other. But if we create a category, an interface animal, we can define some abstract method and then have the implementation. But the specific we kind of when you use the interface, we kind of lose if it's a cat or a dog because we just wanted to talk about animal. And the idea of interface is basically to hide the details and to have a kind of higher level. Instead, in functional programming, we never hide the details. So what we do with the type classes is basically say these types have a kind of similar class. And when we talk about classes, nothing to do with the class is higher, because types is like a class in object-oriented. This is a bit confusing. So type class is a bit like a meta class in object orientation. But with the type class, we said we have a kind of types with a kind of similar way to behave. So we wanted to say something generally about these types. But we don't hide the types. So if we say that the cats and dog both share the mate type class, well, the type class has an instance that allows to mate. That means still keep that cats mate with cats and dogs mate with dogs. And if you think about also when we have the equal method in Java, we can do any object equal to any other object. But probably what we really like is to say that a specific object of a specific class can also be equal to its own class. I mean, it doesn't make any sense to say that an integer is equal to a string. I mean, ideally, we really wanted to have a compiler error. Then there is in object orientation the concept of inheritance, but we don't have inheritance in functional programming, so we don't really have to worry about the high level. But let's skip about type classes. Interface are similar but very different. And type classes have an instance. And it's a way to say that when we talk about sum before, we can say that the sum arrow, we don't say that sum is a monoid. We say that sum has a monoid instance. Because you can create this instance to allow to combine two sum. And also technically, when we talk about our code, the instance will be, well, we see the code, it's probably easy. This is more or less how do you write a monoid in Kotlin with some the laws, basically, to explain the laws. And there is the instance, which is this monoid string. And the monoid string is just an instance, of course, to concatenate a string. Or you can also have a monoid integer that to sum some integer. And you can combine them. Yeah, you can combine also from a list, and then you have in one go. And all these combined methods are methods of the instance. That in this way you can make sure that it works only on the same type. I mean, I know that I'm very quick list, but if there's any question specific, please stop me. Anyway, this is just to give you a kind of idea. Let's pretending that we care about. But now the second entity the second type class that we are going to meet is the functor. And while monoid allows us to combine two arrows, functor basically allows us to transform something into something else. And usually the definition of functor is something that transform arrows from one category to another category. But it also can work in the same category, but still preserving the property. Because functor are more or less like the transformer, so they can transform something in something else, keeping the properties. And the functor is the most important concept of this talk. If you struggle later and you don't know exactly, still try to understand the functor first, because once you understand functor, all the rest kind of fit in place. Everything else that we are talking, basically, it will be functors. Also monads and everything else. And the functor have this kind of laws, also functors laws, and basically say that if you to transform in a functor is doing a map, and you probably already know map because it's already in Java 8 with the streams and another lot of other libraries. But the idea of a map is about functors, so also this talk is about, if you learn a bit about the category theory, it's also a bit easier to understand the new libraries and frameworks. So the idea is that if you have an ID function, and that just an ID function is a function that returns the same value that you put as an input, it must be guaranteed that ID x is equal x. So you cannot have something in map that say, if something, then do something else, or add a value +1 or stuff like that. It must be exactly apply the function to it. And if you are composing two functions, it must be exactly the same result that apply map on one function, and the other function then compose the result. And before London, I was living in Milano. And we can kind of imagine that, to give you an idea of a functor, that we have a functor that move place from Milano to London. So we have the Duomo, the main church in Milano, and we move to St. Paul. The Castello became the Tower of London. Palazzo Reale became Buckingham Palace. But we can also move the arrows. So if we have an arrows that say going from Duomo to Palazzo Reale, our functor must be able to transform this that go to from St. Paul to Buckingham Palace. I mean, we don't care about the details, but this is how functors stay. They translate, but they keep the structure. And also it must be identical if we apply one step to another. I mean, if you go from Duomo to Castello, then Palazzo Reale must be exactly the same result that from Castello to Palazzo Reale, and then from Duomo to Castello. And when we talk about programming, because we said that our programming language is a single category, all the functors that we have basically are the functors in our category, because we are not transforming from one language to another. So those are functions are called end function, because basically they stay in the same category. But even if they stay in the same category, there is a kind of transformation, because that is the functor idea. So what we basically do, we use something, we create a type based on another type, because remember that in category types are the objects. So we take one type that will be like the Duomo in Milan, and we create a new type that will be like the Duomo in London. And what we call generics in Java, in the functional world we call a type constructor, because the idea is that in Java we kind of tend to say something like list of T, whatever is T, like a generic abstraction of a list. In functional world, instead, we focus on the list of T is just a constructor that allows us to construct, to create, to build specific types, like a list of int, a list of string, and everything. What we cannot do in Java, which is a pity for functional programming perspective, is that we cannot say, I want a list of A of a B. Can be like a list of a set of integer. I mean, we can have a list of set of integer, but we cannot leave A and B as generics. We can only have one level of generics in Java. Or in functional programming, what we use a lot is to not specify the second inner level. So we say, this is a list of something that needs something else. So it can be a list of a set that will be of some specific type, or it can be a list of of a specific type, or other stuff like that. And this concept, like a generics of generics, meta-generics, is called higher kind of types. And it's quite useful when you do operation of functor. Because if functor is something that take an A and return a list of A, if you wanted to take a functor, you need to be able to generalize more. And this is something that they are discussing now to put inside the Kotlin. But right now there is a kind of hack, so it kind of works. And this is how functor works. So probably one of the most useful example and you probably already know about, because it's quite useful, is this try. How many of you have heard about the try? Yes, it's basically is an idea of a type class over the exception. So instead of having something that can return an exception, which is something that you remember, the button type, something that we really don't want in functional programming, we use the try, and so the try basically wrap around the computation and can either return a success, like in the first case, or a failure. In this way, instead of returning like an integer, but can be also an error, we can return a try of an integer that will have internally. But the whole point of a functor is that transformation, remember, so let's go back. Another way to see functor is called the lift, the forklift. So if you have a function that goes from A to B, let's say from integer to string, you can have a functor that transforms something that go from fda to fdb, for example, from a list of integer to a list of string. And in this way, basically, we transform the try on of a string in a try of a number, of an integer, which is completely stupid at this example. But if you think that you can take the try from a previous calculation and store in a variable and then transform in another try, it can be actually useful, because you can use the other try to do something else. And okay, this is quite difficult to understand the first time. you can also have a functor, not only over a type, but over a function. So you have a function, in this case, that take a URL and return a connection of the DB, which is something like that you'll do probably with the dependency injection. And what you can do, you can create a functor that is called reader, because it's kind of a typical functor, one of the most famous, most useful. And basically, you do this run that you created a reader with the functor that you want. Then the run basically start the functor, and then you can use the basically transform the result. So you can use this map to get the result that you want. In this case, the username. Of course, the code like this seems quite without any point, but you have to remember that you can compose, and you can pass stuff around, and then you can have the injection of the string connection, for example, in a completely different module that do the actual logic. Okay, another step. So we have the function that transform data. We have the functors that transform functions. So what if we want to transform functors? We have something that is called natural transformation. So going back to our example, if we wanted to switch from London to Paris, we have a functor that goes from Palazzo Reale to Buckingham Palace, and another functor that goes from Palazzo Reale to Versailles, because that is the Paris subcategory. And it's the same with the church. But then what if we want to say, okay, let's take one functor like Buckingham Palace and transform in Versailles. And this is a kind of operation transformation over the functors, which is called natural transformation. And actual natural transformation is something that came before category theory, but is from Mathematica. On the code is something that is quite trivial, to be honest, which is basically we have this try that we talked before, and we can transform this try in an option, which is another type class, or we can also transform the option in a list. So basically, we have a try into a list, and this is a natural transformation. And if the try is a positive value, something like 3 to int is a positive try, is a success try, we have the list with the sign 3. But if it's something that it cannot be transformed in integer, so it will be an exception, transforming in list will be an empty list. Of course, doing this transformation, we lose the information about the exception, for example. In this case, there could be some losing, but the structure is maintained. Okay. Nobody is sleeping yet. What if now we put together the idea of a monoid and a functor that we saw till now? So monoid is about to combine two things, and we can combine the two functor in basically two ways. One is like addition, so we have something of something else. So we have a function inside the functor, a value inside the functor, and we put it together. On the other is we have the multiplication, so we put the functor inside another functor. Let's see the first case first. So basically, let's just look at the last point. If we have a function that from A to B and a functor of A, we can create a functor of B. We can also create, if we have this, the second way is exactly the identical way to, you can transform easily, and it's useful if you have a function with 2 parameters. And for example, with the code, this is, we use that applicative in black is our instance, and we can transform some tries in a tuple of try. So basically, we combine the tuple function have a multiple parameter, and so we can combine multiple functor in a single functor, which is the success or the failure, which it has inside the tuple with all the value. But okay, let's on the other side. What if we did the same things of a monoid, and we have this idea of, okay, let's create a category with all the end functors. We need end functors because we need to compose each other, so it cannot be functor from a category to another. They must work on the same category. So we have all this end functor, and we create a new category with only the end functor. And this is what is a monad. A monad is nothing else that the idea of composing together the end functor exactly in the same way that the monoid compose together the function. And the monad main method are the unity, which is something that allows us to create the monad in the first place. And the multiplication, so something that if you have a functor of another functor of A, we can kind of collapse the two functors and having just a functor. In a kind of mathematical notation, they have this kind of they can mu the multiplication and eta the creation. And they say that the diagram commute, that means that everything must be exactly the same. And these are a graphical way to explain the laws of the monad. And so there is many kind of monads, which are just the most useful and kind of famous one. Nothing prevents you to extend if you have some specific requirement. So each monad basically has the basic monad package, the one that we saw, the creation and the multiplication. Multiplication is called a flat map. And also all the monads are also applicative, so they also have the supply. And also all the monads are functors, so all the monads also have a map. And on top of that, each of these monads has a specific, something specific to this specific monad that allows you to do some operation on a bit more. Probably the most important, at least historically, has been the IO monad, the one from the last, because it's the monad that allows in functional programming to do side effect. For example, if we wanted to read from the standard out, or standard in, or write to the standard out. And that's bring us to the bindings, which is a kind of a dance of monads. That is really the thing that kind of renewed the functional programming around 2000. So, and basically, what bindings allows us is if we have this composition of monads. For example, we wanted to have this IO monad to go to fetch stuff from outside. Then from a student, we want to get the university. From the university, we wanted to get the dean. We have to create this strange, not so nice flat map nesting stuff. But using the bindings structure, we can basically flatten that and be sure that when this final bound of this line, basically, we refer to the previous element. Well, not to the previous element, but to the same IO monad. And let's see a specific code example, which is again with the reader monad. And if you have a function that get the user be given a DB connection, which is that user from context. And note that when we write the get user from context, we really don't have nothing about the DB connection. We just have know that there is an interface, a DB con, that there will be some implementation behind. So this is kind of object orientation hiding stuff. And then when we bind, basically, we can bind together with the space and having something like that, say, user 1 get Frankie, user 2 get Johnny, then combine the two names. And then when this EV that is evaluated, this is something specific to Kotlin. You don't need that in Haskell, but just basically what's happened is that the bindings is creating in parallel. So if it's possible, at least it will fetch both of them in parallel. And then it runs all this stuff. It runs on a specific DB connection that we can define later. But of course, if we return just the first block, just the reader monad, we can define until we call evaluation 1, we don't do absolutely anything. So we can keep composing our logic without going to the database. And only when we have prepared everything, put aside, let's say, and someone else will run the stuff on a specific database, and we get the return. So how we can use morphism in real-world programming? Well, we can still explore. There is really a lot of. One thing that really to think about is that, yeah, purity and all the stuff that we saw is very nice and everything, but is not a goal for us. And perfectly pure programs are perfectly useless. Remember that, I mean, the whole point of purity and immutability is only that allows us to compose the stuff and then run outside. But it's not that pure as some value for say, because at the end we wanted to solve problems, real problems for real customer. And for example, one kind of architecture, not the design that I think that it works quite well, is that if you have this kind of purity bubbles, then you can pass this stuff between actors, and the actors will do some dirty work. This is also, I mean, inspired by Erlang. It's work more or less. So you keep the purity on the model composition, and that's why you want the purity, immutability, and blah blah blah. But when you do actual, you go outside the bubble, then you do the side effect works, and you go to fetch data. So we already arrived to the conclusion. Why functional programming? I don't think it's because code is widget, right? I mean, even after I'm doing this stuff for some years now, and I still struggle to read the code the first time. And so it's not that that's the point. But I'm still quite convinced that is a really good thing. And so this is kind of a comparison. And in left is the good things, and the right is the bad things about functional programming. What I see that when you do functional programming, you start to think much more about the data that you have, the problem that you have to solve. You don't put kind of corner case under the carpet until later. You have to compose this transformation and take all the possible results and try to have types that actually reflect the data that you need. And this definitely comports less bugs and much less testing, because most of the unit tests that we write, I mean, I'm really big fan of unit testing, but most of unit testing is kind of corner cases. So we want to test all the possible corner cases. When we work with functional programming, basically, we tend not having corner case. So doing testing, I mean, is a sum how many kind of different number you want to put, because there is really no corner case that you really want to test. It also simplifies coherency, and I found that you really have less bugs, but you really takes more time to go at that point. And at some point, the state of your program, because we are doing real programs that solve real problems, it's very complicated. That's why I kind of suggest that actors idea that the purity bubbles are not too big, because otherwise you have really struggled to keep a very, very complex state. At some point the state becomes so complicated that it's really a problem to keep. And there has some performance issue, but don't be afraid, because I mean, it's performance issue if you want to do something like a video game or real-time, incredibly fast stuff. I mean, you really want to squeeze out any cycle from the CPU. In that case, functional programming has still some problems. But if you do normal programming, like taking stuff from DB, operating using the output, the overhead of functional programming is basically nothing. I mean, doing a REST API using functional style or not functional style has absolutely no change in the performance. Okay, we assume that I convinced someone about functional programming. What about category theory? I think that if you are kind of serious on functional programming, you should at least give a try to study the category theory, because it's really, really important, and really to learn how to think about and to kind of train your mind on the kind of shape, transformation, and keep all this stuff in your head, which is a very, very difficult. Not difficult, but it's very different from object orientation. And also that is a bit like design patterns in object orientation, that design pattern is something that you should emerge from your code. It's not something that I'm going to write a builder of a strategy of a bridge with a facade, but it's something that your code kind of tends there and then you clean up. In the same way, monads and other type classes should really emerge from your code. So you start writing some functional code, and then you say, hey, this piece, I can simplify and replace all this code with just a monad, because I'm just generalizing on a general concept. Okay, any question? Or this is some links if you wanted to learn more. Okay. Yeah. Yeah. It's quite slow. Yeah. Yeah. Well, that's depend how, this is the same thing that in Scala you do with the for comprehension, in Haskell you do with the do notation, and that's depend how is implemented, how the binding instance is created. And I think there are already in that, I mean, it's going, in that library is also have two implementation. One is parallel and one is concurrent and one is not concurrent. And of course, yeah, also future is a kind of monad if you want, so you can combine those. Okay, thank you everybody. And any question, you can tweet at me or email, blog, whatever.